Good morning. Today I will be presenting Trellis Codes for Periodic Erasures, a journal article by Richard Wesel, Xueting Liu, and Wei Shi, published in the June 2000 issue of IEEE Transactions on Communications. I'm Alethea, and I am a fifth-year electrical engineering major here at UCLA. My lab is the Communications Systems Laboratory, also known as CSL, and my principal investigator is Richard Wesel, who is also a lead author on this paper. Existing error correction codes perform unreliably in the case of periodic erasures. The goal of this paper is to find a Trellis code that will perform equally well for all possible erasure patterns to improve the reliability of communication systems. We hope to improve our ability to detect and correct errors in the case of erasures and avoid catastrophic behavior even when erasures are present. So, why is error detection and correction so important? Well, it's vital for communication systems, memory, and reading and writing data. The reason it's so important is because there will always be issues when it comes to transmitting data. There will always be errors caused by imperfect channels, most importantly by noise. The different kinds of errors that can occur are either flipping bits from 0 to 1 or vice versa, or also what we are calling erasures, which basically occurs when data bits are completely deleted or erased in transmission. The receiver never sees them in the first place. The repercussions of this can be pretty bad. What happens when data is lost? Well, either we can lose the information we intended to send, or we can also lose the error correction bits that enable us to find and correct errors. This schematic kind of shows you what happens in a communication system where noise is present. We have our transmitter here sending this data bit, which is a 0 here, a 1 here. It's just a normal square wave. And when you add in noise, this can be changed so that zeros and ones no longer look like zeros and ones to the receiver, because all of our data bits are represented by voltages. And when you add noise in, it can flip a voltage so that it is no longer received as 0 or 1 as it should have been. By the time it gets to the receiver, therefore, the message we think we have received is not the message that was actually sent. How does error detection and correction actually work? Well, generally speaking, we basically just send extra bits, which introduces redundancy. There's different kinds of redundancies we can introduce, but some common ones are the parity check, a cyclic redundancy check, also known as a CRC, and pilot symbols, which are basically predetermined patterns of bits that are sent, and when the receiver sees that, it knows that, therefore, that's where the data starts or ends. We won't really be going into CRCs or pilot symbols today, but I just wanted to go over a simple parity check scheme so that you kind of understand how this kind of thing works. So basically, this original message here are these white bits, and our parity check bit is this 0 in dark blue. The parity check tells you if you have an even or odd number of ones in the message. So if you have an even number, here we have 4, then you'll have a 0. And if you had an odd number, for example 5, you should have a 1. However, let's say that in transmission, this final 0 in the data message is flipped to a 1. Then your parity check will still be a 0, and you'll know that you have an error because you have an odd number of ones and you have a 0. So they contradict each other. However, this is a pretty simple error detection and correction scheme, and it doesn't always work. As you can see, if 2 bits are flipped, so let's say this 1 and this 0 are flipped to the opposite bit, as you can see in red here, then the parity check will still be 0, and you will still have 4 ones, in which case the parity bit and the number of ones are consistent, so you might think there isn't an error, even though we know that in fact we have 2 errors. Why are erasures in particular so devastating? It's because they can lead to what we call catastrophic behavior, even in normally robust codes. Basically, a catastrophic behavior is when a finite error leads to an infinite number of bit errors, which makes it impossible to correct the message. Here's how periodic erasures work. Basically, erasures are message bits, as we said, that are erased or lost in transmission. Periodic erasures occur when we have repeating patterns of these erasures with a set period. For example, this here would be a period 5 erasure with a pattern 00101. As you can see, here's 1 period, And here's the second period of the same pattern, and this is the first 3 bits of the third period. The zeros here represent the positions of erased bits. They are not actually 0 bits. They just represent positions of bits that will be deleted in transmission. So for example, if you have this data message here, and we apply this period 5 erasure pattern with the red bits representing which bits will be deleted, we can kind of overlay and see 0, 0, 1, 0, 1, 0, 0, 1, 0, 1, etc. So these red bits are going to be deleted, and this is what you receive. Clearly, if you start with this message and you end up with this message, you're going to lose a lot of data. If not information, you will certainly lose a lot of ability to correct errors. Possible causes of periodic erasures include channel interference from partial band interference of channels that are very close together interfering with each other, or malicious jamming in the case of, for example, a military scenario where one country wants to stop the communications from another. So before I get into the final results from the paper, I just wanted to kind of go over how you measure the effectiveness of your encoder and decoder. Basically, one of the main ways to figure out how good your communication system is to look at the signal-to-noise ratio, which is the level of the transmitted signal versus the noise. Obviously, you want the level of your transmitted signal to be much higher than that of the noise so that you can actually decode the signal and make out what it is. The channel mutual information is a little bit more technical, but it basically measures the information gained about the input by looking at the output. In a noiseless channel, where there is no noise present, so presumably you don't really have errors, all information is mutual because the input and the output should be the same. Finally, we can look at the bit error rate, which is just the number of bit errors received per unit time. So this paper looks at 2 different encoding schemes. Trellis coded modulation, which is bandwidth efficient and it's a rate 1/2 encoder. We'll talk about that more in a second. And Reed-Solomon, which it just uses as kind of a comparison because Reed-Solomon is a very good encoding and decoding technique used by NASA because for satellites or anything transmitting from space, you necessarily can't transmit with very much power. And transmitting at such a far distance means that you're going to have a lot of errors, which means that your error detection and correction is very important. Trellis coded modulation. This rate 1/2 encoder just means that for every 1 input bit, you output 2 output bits. Basically, for every input bit, you will also have the same number of encoding bits for error correction and detection. The trellis basically works like this. This is kind of a visual diagram of how it works. You can imagine 0, 0, 0, 1, 1, 0, and 1, 1 as states, where you imagine a state to be kind of the position of the system. For example, if you had a light switch, in one state, the light switch would be on, with the light bulb being turned on, and in the other state would be off. The trellis goes forward in time from left to right, and each of these solid lines is an input of a 1 being pushed into the system, and the dotted line is an input of a 0. So basically, if you're in the 0, 0 state, which you could say is maybe 2 lights both being on, then if you get an input bit that is a 1, both lights will stay on. Let's say that this third state is both lights being off, then if you got a 0, both lights would be off, etc. So, findings and conclusions. We can see from figure 7a that our bit error rate and signal-to-noise ratio differs a little bit for different erasure patterns. This is one trellis code, known as code 13 in the paper. However, that variation is pretty small if we actually zoom out and look at how it looks compared to the Reed-Solomon code acting on the same erasure patterns. You can see that the Reed-Solomon code behaves very differently for the 6 different erasure patterns, whereas the trellis code is all pretty much in the same area, which means that it's going to be much more reliable for all the different erasure patterns, which is really important because we can't always predict what bits are going to be erased by the channel, and so this trellis code is going to be much more reliable in general. Further research from this paper. Currently, my team is actually working on a project that is a follow-on to this paper. Basically, we are intentionally creating erasures Here we call it puncturing instead of erasure since we are introducing them on purpose. We are still using Trellis Codes because they do perform better and more reliable for puncturing or erasures in general. We are also using feedback via ROVA, which is the reliability output Viterbi algorithm, which basically gives you a probability that the output that you decode is correct. The reason we use this is because initially we're going to puncture or get rid of as many symbols as possible, which allows us to basically send a much fewer number of bits and is much more efficient therefore. However, then our ROVA algorithm will tell us there's an 80% probability that this is correct, and say we want a threshold of 99.2% probability that it is correct, we can unpuncture, basically send back to the transmitter and say, I want you to add this bit back in, and send the message again until our ROVA algorithm says you've got a 99.2% chance that this output is correct, and then we can stop. We also want to add list decoding, which is basically a very good way of correcting errors because it gives all of the possible outputs accommodating for errors that could, or rather, sorry, all of the possible inputs that could occur from the output we see. It improves our correction abilities, but because you have to compare to so many different options, it is very inefficient. So we're looking to impose a maximum list length to improve that efficiency, which basically will cut down the number of possibilities we are comparing to, since we assume that if we are flipping too many bits, we're probably creating more errors than we are correcting. We can therefore ignore a lot of those options. Why should all of this matter to you? Because error detection and correction matters for broadcast TV, streaming, 5G and cell phones, satellite communications, military communications, memory data and storage, and sending lots of data at once, which is nothing too crazy. Even just streaming video on Netflix or Disney Plus sends a lot of data all at once. The modern world runs on digital communication systems, so having good error detection and correction is the name of the game. Here's my list of references, and I also wanted to give special thanks to the Communication Systems Laboratory and my wonderful team, Dean Richard Wesel, my PI, Alex Baldoff, my DLS, and my teammate Shake, who's just wonderful in all the work we've been doing lately. Thank you.